Hey, Vlad here, DevInsider.com, and welcome to the second part of the video about recursion. Okay, it's the sort of the 8th video in the Scala playlist. So we're gonna jump straight into the virtual machine where we left off right here. Okay, so this was the example that I used just to explain the concept of recursion, and today we're gonna actually have a different example. Okay, so let me have one window over here, and let me just collapse method 1. Collapse method 2. We're not going to be playing with them today. Method 2 and method 3, and it doesn't matter which one we're calling. In fact, let's not call any of them. Okay, so this is what we have. Let me string sublime again. So we have our revolver running in SPT, the same as in part 1. And what we're going to do today is we're going to play with two mathematical functions. One is called factorial, and the other one is called Fibonacci, or the Fibonacci numbers. And in fact, I really have to include them, because if I don't include these two mathematical functions in a video tutorial about recursions, then nobody's going to believe me, right? Nobody's going to believe me that the recursion actually works the way it works, because these two are basically in literally every computer science book, and every tutorial, and everything that mentions recursion, we have those two functions. All right, let's recap some math. If you add some numbers together, then the end result is called a sum. And if you multiply things together, then the end result is called a product. So imagine a task. If I give you a number like 20, and I ask you to go through all the numbers from 0 to 20 and just to add them together to calculate the sum. Well, factorial is exactly the same thing, but instead of addition, we're doing multiplication, right? So we're just going from 0 to 20 in this case, just multiplying everything together, and we want to see the product. So what we have here is the Wikipedia page for factorial. Now let me zoom in a little bit. Actually, let me zoom in a lot. Okay, so in mathematics, the factorial of a non-negative integer n, denoted by n and bang, is a product of all positive integers less than or equal to n. For example, the factorial of 5 is 5 multiplied with 4, multiplied with 3, multiplied with 2, multiplied with 1, and it's 120. So in their example, they have a 5 instead of a 20. And the value of 0 is 1, according to convention for an empty product. We can ignore that. But basically, the factorial of 0 is 1, right? So factorial is a very recursive function, right? So so look at this. So the factorial of 5 is actually 5 multiplied the factorial of 4, right? And the factorial of 4 is 4 multiplied with the factorial of 3. And the factorial of 3 is 3 multiplied with the factorial of 2. And the factorial of 2 is 2 multiplied with the factorial of 1. And 1 is just simply defined as 1. 1 times 1 is 1, right? And 0 is also 1, right? So it turns out that we can actually just simply write this down, okay? So in the case of 0, it's 1. Let's do that. So we're going to have def factorial, right? And it's going to take an integer, right? And it's going to return an integer, okay? And we're going to do this. If n equals 0, and I prefer to do it like this so that it looks like a function invocation. If n equals 0, we're just going to return 1, okay? Let's go back to Wikipedia, right? So if n is 0, then we're just going to return 1. And now all we need to do is, remember, if you wanted to calculate the factorial of 5, we would need to multiply 5 with the factorial of 4, right? So if you wanted to calculate the factorial of n, we would just need to multiply n with the factorial of n minus 1. And let's just do exactly that. So we're going to have else. We're just going to multiply n with the factorial of n minus 1. And it turns out that we're done. Now it barks at us because we're not actually calling factorial, so let's call it. Let's see factorial of 0, of 1, of 2, of 3, of 4, and of 5. And if at 5 it gives us 120, then we did the right thing, okay? 120. Before we continue, I'm going to modify our print line a little bit. So over here, I'm just going to do a 0 and an arrow plus and a space over here plus factorial of 0, right? And I'm just going to have a print line after that, right? And I'm going to do this for everything. So basically what I want to see is this is the argument that we're passing into factorial, and it's getting mapped to the result, right? So we're just going to have like some sort of a table, right? And let me actually do this for all the others, and let's do this until 8. All right, so now we have all 8 of them, and this is exactly what we have, right? So factorial of 0 is 1, factorial of 1 is 1, factorial of 2 is 2, 5 is 120, 6 is 720, 7 is 5040, and so on and so on. And as you can see, it grows like crazy. It's a very scientific term. It grows like crazy. Now, after factorial, we're gonna play with Fibonacci, and for Fibonacci, it's very important to see how many iterations we had, right? Because over there, it's a bit more complicated. So we don't really need it for that thing, but I'm still gonna do it. Right, I'm still going to do it so that you can see the transformation, and the transformation is exactly the same as we had in the previous video, right? First, what we're going to do is the variable is going to be called x, right? It's going to be called x, right? And the factorial is going to be called loop. You know, we already did this in the previous video, right? And now we're just going to do this, and around it we're going to have the actual factorial that is going to take the end and produce an end. It's going to open here, close over here, and the last thing that it's going to do is going to call loop with m. We're back to the same thing as we had before, and by the way, notice that this is not a Taylor recursive function, right? We discussed this in the previous episode. As column annotation dot tailrec, not cool, okay? Not in tail position. All right, but we already knew that, and in fact, we're gonna convert this into a tail recursive function. This is also one of the reasons why we're here. Okay, but first let's count the iterations. Iterations 0, and the first thing that we're gonna do here is gonna say plus equals 1, and over here we're just gonna store the result, and we're gonna print out the iterations, and then we're gonna return the result. Right, so now we have the same table, but we also see how many iterations we went through, right? So for example, in order to calculate the factorial of 5, right, and the result is 120, we actually need 6 iterations, right? So only for 0 we needed 1 iterations, right? Because when it comes in with a 0, it just jumps right out of it, right? It comes with a 0, increments us to 1, right, and then just jumps right out of it. Okay. But for 1, it actually needed to go down here. This can actually be optimized, right? Because we can say if x is 0, return 1. Otherwise, if x is 1, also 1, right? Oh man, how did I do that? Else if, there we go. Right? So this can be optimized. Now, also for the 1, it needed only 1 invocation. Sorry, I pointed to this one. I meant over here, right? So we have 1 invocation for the 0 and one invocation for the 1. In fact, maybe we should do invocations like this. Whoops. I call it iterations. Let's do iterations. Iterations. There we go. Right? So now it's more visible, right? So iterations 1, 1. Okay, but we don't really care about this. Let's just remove that, right? So now we're back to 2 iterations for 1. All right. So before we continue, notice that in this case we don't have an endless loop, right? If we give it a big enough number, right? So let's remove all of that, and let's just do print line factorial of 9999. Wow, it looks like we got 99,999 problems, but math ain't one. Okay, so we produce a Stack Overflow. Okay, so it turns out that there's a tail recursion version of factorial, and this is what we're going to do next. Okay, it is a very similar problem to the one that we had in the very beginning. You know, even though we were building the whole stack, we actually don't need the information of every stack frame. We just need one variable. We need to keep track of only one variable, right? And we gotta call this variable accumulator, right? And the convention for this is to do this, accu, right? And that's why the first time we're calling it, we're gonna call it was 1, right? And then instead of doing that, right? So first of all, we're always gonna return it, okay? And then instead of having this as the last call, we're gonna have the loop as the last call. And the first argument is still the same, right? The x remains the same. It's x minus 1, and the other one is the actual multiplication, right? Now I understand that this is not the most this is not like the best way to explain this. In fact, I didn't really explain this, but I don't know, maybe it's going to be a bit more evident if you do this. You know what you should do? You should rewrite this thing with a while loop, and you will see, maybe it will become more clear how this is happening. So what we see on the right is that no Stack Overflow is happening all of a sudden, but we see a 0. We're going to talk in the next video why it was a 0. Let's just remove this line, because this line was just there so that we can see that no Stack Overflow is produced, right? So let's just remove that, and let's just do this, right? And now we should see exactly the same result, but this time we have a tail recursive function. There we go, Scala annotation tail rec. Everything is still fine. The results are still the same. Everything is awesome. Now, what we did here is a so-called programming technique called memoization. It's like memorization, but there is no R, right? Memoization, okay? And what it's basically doing is it just keeps track of the results that are needed for the future call of itself, right? So memoization and dynamic programming are both techniques for things like this. And memoization very, very often, in its simplest form, very, very often leads to tail recursive calls, okay? By the way, don't confuse dynamic programming with dynamic type systems. So with dynamic languages that are introduced in the video number 4, I believe, about type systems. It's a completely different thing, right? It's a very advanced topic though, so we're not going to talk about it. All right, so we're basically done with factorial, and as I said, please look at this and write a version with a while loop. It should look exactly the same thing. See, basically you're gonna keep track of this variable, right? So you're gonna have var aku, right? And instead of passing it all the time through the stack, right? And having Scala convert this whole stack, a bunch of stack frames into a while loop. Instead of having that, you're just gonna have your own variable, and you're just gonna override it. You basically gotta have like literally exactly the same code over there, right? Because of the name parameters, it's going to look exactly the same. I basically just wrote it for you, right? But still, please try to do it. Then it's just going to, click in your head, and you're going to understand it, right? Okay, so the next thing that we're going to do is we're going to talk about the Fibonacci numbers. Now, the Fibonacci numbers, they're going to start very similar like factorial, but Fibonacci, like if factorial grows like crazy, then Fibonacci grows like freaking nuts, okay? It's just insane, okay? And this is exactly why we have it here, okay? To also to show you how many iterations, right? Because over here, the result grew like crazy, but the iterations actually didn't, right? So if you want to calculate the factorial of 1000, well, you need 1000 iterations, maybe 1001, maybe 999, depends on the 0 1 thing. But for Fibonacci, Now the Fibonacci numbers are related to the golden ratio and stuff, right? So there are two versions. One starts with a 0, the other one starts with a 1, and the definition is very simple, right? So the definition of Fibonacci is basically you give it a number, and what it's going to do is it's going to calculate the sum of that number by sorry, not the sum of that number. Yeah, it's going to calculate the sum of the number by adding the previous number and the one before that. So basically the previous two numbers, right? So by the way, notice when we're going to convert it later into a tail recursive version, this is what we will need to keep track of. We're going to need to keep track of the previous number and the one before that, okay? So it has two seed values, right? So factorial had 1. It was saying, okay, if it's 0, then it's 1. Fibonacci has 2, right? So we're going to implement a version that has that starts with a 0, right? So Fibonacci of 0 is 0, Fibonacci of 1 is 1. So we can have basically exactly the same algorithm as for factorial, exactly the same beginning. Let me collapse factorial. Okay, so let's gonna have a Fibonacci. Also, by the way, notice that in math they always use the same letter F for a function, right? In programming, we're not afraid to use a few more keystrokes. Okay, so Fibonacci of n is gonna be the same thing as in factorial, right? So we're gonna say if n equals 0, then what was it? It was 1, I believe, right? Was it 1? No, 0 is 0 and 1 is 1, okay? So Fibonacci of 0 is 0. Otherwise, if it's 1, then 1, right? And otherwise, it's just the sum of the previous one, right? So it's a Fibonacci of n minus 1, sorry, plus Fibonacci of n minus 2, right? And over here, we're just going to do what we did with factorials, just going to do Fibonacci. Right? So now we have the Fibonacci sequence over here, and we can compare it with that thing, right? So we have the one that starts with a 0. So we have 0, 1, 1, 2, 3, 5, 8, 13, 21, right? So the 8th one is 21, right? So this is the one we have, and we're not going to need Wikipedia anymore. All right, so what we have here is we have two recursive calls, right? And obviously it's not tail recursive, right? Let's demonstrate that by doing Scala annotation.tailrec, right? And obviously it's not tail recursive because of this plus. You can see, like, I don't know, maybe if you're a beginner you can't see it, but it's really obvious, okay? And also because, as I already mentioned, like in almost every tutorial and in almost every book, they talk about factorial and Fibonacci. So now we can write this thing down in our sleep. Okay, all right. So we're gonna do the same trick as we did before. Okay, so we're gonna turn everything into x, and everywhere it says Fibonacci, we're gonna do loop, right? And over here we're gonna do Fibonacci, and it takes an end. And come on, what's wrong? Produces an end, right? We're gonna have a scope around loop, okay? So we're gonna have that, right? And as the last thing, we're just gonna call loop with n. It should be n over here, right? There you go. So now it should be exactly the same thing, and now we can count our iterations, right? And in fact, maybe we can just do this. We bring down iterations. We bring down iterations plus 1, and we can actually do this over here, right? Because it's exactly the same thing, and we're calling it with, oh no, this was the recursive one, right? So we're just gonna have n, okay? Exactly the same thing, but now we see the iterations, okay? And now you can see that the iterations grow like freaking insane. So it's actually a tree of recursion, right? So just to calculate the factorial of 6, right, we need 25 iterations. To calculate the factorial of 8, we need 67 iterations. In fact, let me do this. Let me do that. Let's go for Fibonacci. By the way, I might have confused Fibonacci with factorial a few times because they both start with F, and they always confuse people. Right. Anyway, so let's do Fibonacci of 25, and let's see if it's actually going to work. So as you can see, it calculated it kind of fast, right? So the Fibonacci of 25 was 75,000 something, but it needed a lot of iterations. It needed 242,000 of iterations. Let's go to 30 and let's see what's going to happen. All right, 30 is still fine. Let's go to 35. Still fine. All right, let's go to 40. All right, it took already a while. Let's go to 50. All right, now we're talking, and this is exactly why we're here. Now it's doing and doing and doing and doing. By the way, notice that when it's gonna finish, SPT is gonna tell you exactly how long it took. So first of all, we're gonna see the iterations, right? And the number of iterations is probably going to be correct. No, it's for sure it's going to be correct, unless it overflows, but it shouldn't overflow, right? So the number of iterations is going to be correct, but the result is not going to be correct for the same reason as the factorial of 99999 wasn't correct. But we're going to talk about this in the next video, okay? So I'm sort of thinking if I should cut it out or I should not cut it out, and I want to actually let you see how long it actually takes, so that I can drill this into your brain. The tail recursion is very important. Or if you're in Java and you don't have tail recursion, that these algorithms are not really efficient, right? So math does not really care about things like this. So mathematically, this is a perfect valid definition of Fibonacci, but as a programmer, you have to care about many more things, right? As I made this joke in the no, I actually made it in this video, right? Just a few minutes ago. It looks like we have 99 problems, but math ain't one, huh? All right, so it should not take longer than 1 minute. So I'm just gonna cut it out. Okay, but I actually want to see this being calculated. All right, so it finished, and I'm really sorry, but it does not give you the time. I believe that probably the regular run would give you the time, but this one doesn't. Hold on, maybe we can press enter. No, still. Anyway, it took a minute or maybe two actually, and look how many iterations it needed. Fibonacci of just 50 needed, hold up, so this is okay, it needs 2,075,316,483 iterations, right? This is insane. This is also one of the reasons why Fibonacci is part of every computer science book. Okay, all right, so let's go back to doing this, and let's remove that. And oh my god, Revolver is so awesome, right? I just sent it into this 2-minute long calculation and just kind of kill it like this. It's freaking awesome. All right, so we're back at this, and now we're gonna have a tail recursive version of that. Now I'm going to warn you, the tail recursive version is not simple, right? Even the one for factorial was not simple for beginners. So play with this and do the same thing. Implement it with a while loop, right? So as I already mentioned, we're going to need to keep track of basically 2 accumulations, right? So we're going to have AQ1 and AQ2, AQ1 and AQ2, and they're both integers, right? Integer and integer. And these are basically the same as for factorial. See, once we introduce this thing, then we were returning returning it in the 0 case, right? That's over here, and in the second one we're going to return the second one, right? So you can really clearly see the symmetry. And before in the factorial we had a 0 over here, and now we have a 0 and 1 here, and then we call loop over here. The first one was a 1, so over here we have to do exactly the same thing as we have for Fibonacci. So the first thing, this is basically from the definition, right? So the factorial of 0 was 1, the Fibonacci of 0 is 0, and the Fibonacci of 1 is 1. So this is basically the definition. This rewrite is almost mechanical, right? So we have that, okay? So now we're just gonna get rid of this. So instead of that, we're gonna have loop, right? We're gonna just have a loop, and we're gonna call it once. So we're gonna do this, right? So the x is going to become x minus 1, right? Because for Fibonacci is exactly the same thing. Was this going back? You know, in order to calculate Fibonacci of 50, you need to know the Fibonacci of 49, and you need to know the Fibonacci of 48, right, and so on, right? So we're basically, you know, going back. So this is the going back of the first number, and this is the going back of the second number. So AQ1 is going to become AQ2, right? So this is the going down of x, and this is the going down of AQ2. So we have to, you know, move them both at the same time, right? And this is the actual, you know, the actual definition of Fibonacci, right? We're just going to add the last ones together, the ones that we memoized, right? So if I did everything correctly, and it looks like I did, everything is still fine. So now we have a tail recursive version. Scala annotation tail rec. All right, we're gonna have the tail recursive version, and now look at this. Click. And we're gonna have a Fibonacci of 50. Boom, done. Right now the result is wrong again, but we needed only 50 iterations, right? We were just calling each other over and over and over and over again. Okay, so play with this. You know, have a while loop. Do the same thing with a while loop. You know, you're gonna have 2 variables. You know, they're gonna be outside of this loop. They're gonna be over here, and it's literally the same code, right? It's literally the same code. This is why, you know, Scala can mechanically convert it into a while loop, and I wish a bunch of other languages could do that as well. All right, so now you know most of the things about you know, related to recursion. It's obviously not all of them. And by the way, I was talking like really fast in both of these videos because I knew that they would get like really long. This is why I ended up splitting them into 2 parts. Yeah, so I'm sorry for that. You know, YouTube has a way of playing the video a bit slower. So if you're not, you know, not a native speaker, maybe you can turn it down a little. All right, so I hope that your brain is not melting, because recursion is a very complicated topic. As I already said in the beginning of the first video, you know, recursion is very complicated. Beginners hate it. So I'm sorry if I let your brain melt a little. It wasn't easy for me as well when the first time I learned it. And in fact, it wasn't even easy to prepare for this video, right? Because I had to find, like, you know, super simple example, you know, the simplest examples possible, and I was going through the script like 4 or 5 times. It took me longer than 9 hours. So I hope that I managed to explain it to you. If you have any questions, you know, hit me up on Discord, and yeah, see you next time. The next video is not going to be as complicated as this one. This is probably one of the most complicated ones in the next few weeks. All right, I hope you liked it. You know, press the like button if you did, and subscribe if you're new here, and cheers.